Hello everyone, welcome back. This is Theory of Computation, another prerequisite video here. Today we're talking about sequences and tuples. So if you're not already familiar with some elementary set theory, then I would advise that you have a look at my previous video, which is basically just all the stuff you need to know, all the prerequisite content on set theory that you're supposed to really know before we get into the main sort of theory involved in the theory of computation. And this will be the second video. There'll be a few more videos. There's there's quite a few sort of mathematical things that you don't need to get used to. I'm going to sort of do one topic per video, really. So I was initially going to do two, and then I realized that took a while, so I thought it'd be better to do one. Also, I want to apologize for being quite slow on uploading. I'm quite busy in my life at the moment, so uploads are very much dependent on when I have time. Another thing someone said to me is that this is way too light. Like the background is way too bright. So I want to see if I can change that. Okay, so this should be a little bit better than a little bit easy to see because someone told me that my board is way too bright and that no one could actually read it. So here we go. So this is sort of change of scenery here. Anyway, today we're going to be talking about sequences and tuples. Okay, this is still prerequisite content. So if you're already familiar with this, then just skip ahead to when I release sort of future videos. If you're unfamiliar with any of the other prerequisites, go check out those videos if they're released. And if you're fine with everything, then just go straight ahead to the first video on the actual proper theory. Although obviously at this point in time it won't be released, but when it's released, go and check it out. Okay. At the time of recording. Okay, anyway. So we're going to talk about sequences and tuples. Okay, so this sort of follows on very nicely though from sets. Okay, so the concepts here link in quite nicely with set theory. Okay, and there are some key differences that you need to be aware of in terms of differences between sequences and tuples and sets. Right, so the differences between those things should be, that should be something that you get out of this video. Okay, and you should also get out of this video what a power set is, what the Cartesian product is. Those are really the main things that I want to talk about. But without any further ado, let's get straight into it. Okay, so first of all, what is a sequence? Okay, so very much like a set, a sequence is kind of just like a collection of objects. Okay, so we can define a sequence as follows, right? For our sake, anyway, a sequence of objects. Okay, and obviously I use this term very loosely, right? Objects sort of makes you ask what is an object, but in a sense, an object is kind of whatever you want, right? You just sort of define it, right? So if you wanted to have a sequence of cars, you could define a car to be represented by make, model, etc., and then just place that as an object into your sequence. So it's very much open to your own sort of definition as to what an object is. Okay, so open to interpretation. But yeah, I mean, hopefully you can understand just generally that a sequence of objects is a list of those objects in some order. Okay, is a list of those objects in some order. Okay, so it's not necessarily clear what the difference then is between a sequence and a set just from that. Although there is definitely some emphasis on the fact that they are in some order. Okay, obviously for sets you should know that the order in which I place my elements for a given set is irrelevant, right? So the set containing the elements 1, 2, and 3, right, is equal to the set containing the elements 2, 3, 1 in that order, right? So the order of the elements is irrelevant. Okay, but the fact that I've defined a sequence by saying that it's a list of objects in some order is basically saying that this is important, right? This fact that they're in some order has to be important, because if I were to find a set as effectively a list of objects in some order, that wouldn't be quite right, because there's not really any inherent order for a set, right? Whereas for a sequence, well, as we'll see, the order does matter. Okay, so there is some inherent order. So that's really the point that I'm trying to make with this definition here, or where the textbook is trying to make this definition. Okay, obviously with a set, you should already be familiar with this sort of notation. So these sort of braces here, and then maybe A, B, C. So this is sort of just set notation. Okay, but of course, there also sort of has to be different notations and different mathematical structure, I should really say. Or really, I guess it is an object in some sense, right? Because you can put a sequence inside another set or something, right? So sequence is also another object. So we need our own notation for these sequences, right? And so that's the next thing that we should introduce. Okay, so we usually designate a sequence, right, by writing the list inside brackets. So I'll say the list, obviously I'm just referring to sort of this, right, what we're talking about up here, right, just a list of objects inside brackets. So this time specifically it has to be sort of these brackets, so like this, instead of the sort of braces that we used for sets. Okay, so that's really the difference that you need to be aware of. Okay, so we can designate a sequence, so we can basically assign a specific sequence by writing effectively the sequence of the list inside brackets, right? And so that will basically specify which sequence we're talking about. Okay, so as an example, the sequence of objects 7, 21, 57, right, would be written as effectively open bracket 7, 21, 57, close bracket. Okay, right. And yeah, and of course, importantly, this is not equal to the set containing the objects 7, 21, and 57. Those two things are different, okay? And we'll get into the details again in a second. But ultimately, the order of terms in a set, there's no inherent order, right? Whereas with a sequence, there is, okay? So the order is specified here, right? So the order is specific. 7 first, then 21, then 57, okay? And if I swap 21 and 7, then I have a different sequence, okay? So that's what I really mean when I say we designate a sequence by writing the list inside brackets. Because we are just, like, sort of specifying which sequence we're talking about by writing it out in this form, right? Whereas with sets, we're not necessarily specifying. I mean, we are specifying a set when we write it out in this form, right? But there's obviously there is no inherent order, so we're not ever specifying an order. But I guess yeah, we still are designating a set by writing it in this form. So yeah, effectively the point is this is just how we write sequences. Okay, and yeah, as I've just been saying, the order of terms in a sequence does matter. Okay, so it does matter. Okay. On the contrary to order of terms in the set. So as opposed to the order of terms in a set. Okay, I'll write that instead. As opposed to the order of terms in a set. Okay? So that's sort of one of the differences between sequences and sets, okay? So the order of terms does matter, okay? Another thing is that the repetition of terms does affect the sequence that I'm talking about, okay? So repetition of terms also matters for a sequence, but obviously not for a set. Okay. So to consolidate this effectively, we have obviously the sequence then 7, 7, 21, 57. So that's a sequence, right? I've just specified it by writing the terms in that order within brackets. So that sequence is effectively different from the sequence containing the objects 57, 7, 21, right? And also the sequence containing the objects 7, 21, 57, right? So I'm not sure why I use those two examples in my notes. I mean, they're pretty much the same thing. But ultimately, this, right, has a repeated 7 in it, okay? And so that, right, if you were dealing with a set, then any set that has a repeated 7 in it, so the set containing the elements 7, 7, 21, 57, is just equal to the set containing the elements 57, 7, 21, right? Because repetition of elements doesn't matter, and the order doesn't matter, okay? But that's not true at all for sequences. Okay, in sequences, repetition of terms does matter, and the order does matter, okay? So, the fact, effectively, that I have a repeated 7 here makes it different from, for example, 7, 21, 57. Because even if the terms are in the same order, right? Repetition of terms does matter. So adding an extra 7 changes the sequence. So I think that's why I probably did that. Because in this case, the terms are in order, but there's not an extra 7. So obviously it highlights that in that case, obviously that's going to be completely different to what we have here, right? But in this case, the order is different, and there's no repeated 7. So, I mean, so as you would expect, right, it's completely different by our definition. Okay. Right. So obviously, we can have finite sets, we can have infinite sets, and so similarly, we can have finite sequences and infinite sequences, right? So sequences may be finite or infinite. Right. And actually, in general, we actually give another name to finite sequences. So finite sequences are generally known as tuples, okay? So finite sequences are often called tuples, okay? That's just sort of I guess, the way that we've sort of worded these things, right? It's just the convention that we use. Okay. Right. And just another sort of convention is that a sequence containing k elements is a k tuple. So a sequence with k elements is obviously a finite sequence if it has k elements or k objects, right? So a sequence with k elements or k objects is a k tuple, right? So because it's finite, first of all, it's a tuple, and to represent, so because it has k things inside it, we say it's a k tuple specifically, okay? So that should make intuitive sense, right? There's a finite sequence with a tuple, and it has k things inside it, so it's a k tuple, right? Fairly standard. Obviously, as an example, we have our earlier sequence, so the sequence containing the objects 7, 21, 57 in this order, is obviously going to be, therefore, a 3 tuple, right? It's a finite sequence, there's only 3 things inside it, and there's 3 things inside it, so it's a 3 tuple, right? So finite sequence means tuple, and 3 things inside it means 3 tuple. Okay. And we have, again, just another special name, even more special names here. Effectively, a 2 tuple is effectively also known as an ordered pair. Okay, so any sequence with just 2 elements in it in whatever order, so like A, B, like this, is known as an ordered pair. Okay, and again, it kind of makes sense why it's called an ordered pair, right? Because the order of things matters, okay? And I believe that we did also see with sets an unordered pair, right? In which case you just have a set containing elements A, B, right? Because in that case, the order of the term doesn't matter, right? So you can sort of swap these two and it doesn't change anything, whereas in this case it does. So hopefully that's starting to make sense then why, the motivation for like why we're naming things this way. Okay. And something else that you might see is us actually placing, for example, sets inside other sets. Okay, so obviously all that we sort of said is that a sequence, for example, or a set is just kind of a list of objects, right? Obviously with the order mattering or not mattering, depending on whether you're talking about a sequence or a set, right? But the objects themselves, it's vague what that means, so it's up to interpretation. And in reality, we actually say that a sequence itself is an object, and a set itself is an object. So if a set is a list of objects, and a set is itself an object, then it could indeed be a list of sets. So you could have a set of sets, or you could have a set of sequences, right? And so that's sometimes something that you might see in practice, right? So another point here, sets or sequences, right, may also be found within other sets or sequences. May also be found as elements within other sets or sequences. Okay. Okay, so now it's about time that we introduce effectively the power set. So if you've done sort of set theory before, it's probably something you're used to. I'm not sure why they actually chose to introduce it at this point in time. But effectively, now that we know obviously that we can have sets and sequences as elements or objects within other sets and sequences, right? We need sort of, you might ask what's an example of this? And probably the most famous example of this is the power set, right? Which does occasionally come up. Okay, so what is the power set, right? So the power set, this is how we define it. So the power set of a set A, we'll say of a set capital A, right, is effectively the set of all subsets of capital A, right? So if you're not familiar with that terminology in terms of subsets and just what a set is or anything like that, then please go back to the previous video, okay? So you need to be, I'm assuming you're familiar with this concept of subsets and things like that, right? So the power set of a set capital A is a set of all subsets of capital A, okay? So I'm assuming that I've also written here an example. Yeah, here we go. So let's look at an example of this, right? So as an example, imagine that I have a set capital A, right, which just has the elements 0 and 1, okay? Then the power set of A, right, power set of A, and sometimes you denote that with sort of like a P, funny P of A, if I remember correctly. I mean, that's kind of up to the way that some people write it, but yeah, you might see sort of some P of A notation to mean effectively power set of A. I think it's a funnier P than that. I don't know. At least when I first was introduced to the power set, there was like some really interesting notation for it. But effectively, I'm just going to denote it with this P of A here. So the power set, right, I should say then the power set of A, right, denoted P of A like that. It's effectively just going to be another set, but it's going to be the set of all subsets of A. So first of all, which subsets of A do we have? Okay, just think about that for a second. Well, evidently the empty set, right, the set with 0 elements is going to be a subset of A, okay? Because a subset is just defined such that every element within my subset is also in. So if, for example, if A is a subset of B, and remember we have this notation for it, if A is a subset of B, okay, then effectively every element in A is also in B, right? And this also includes the possibility of the two sets being exactly the same, whereas a proper subset doesn't. That's really the difference between those, if you remember that. And so, effectively, if every element in A, in the set A, capital A, is in the set capital B, then capital A is a subset of capital B. So in this case, we have capital B, which is the power set of capital A, right? Oh no, sorry, no. In this case, actually, we have capital B, which is just capital A, right? Our capital A, and we're saying that the empty set is a subset of capital A. The reason is because every element in the empty set is also going to be in capital A, because there's no elements in the empty set, right? There's no object in our empty set by definition. It's a set with 0 objects, 0 elements in it. So every element in it must also be an A, because there's nothing in it, right? So it's sort of just one of those cases which is a bit weird. But there we go. Okay. And some other subsets that you might notice are, for example, the set containing the element 0. This is a subset of capital A because every element in this set is also in capital A, so 0. The element 0 is also in capital A. And then you also have the same but with just 1. And then lastly, you just have the set that you started off with, right? Because every set is a subset of itself, right? Because by definition, every element in itself is in itself, right? So effectively, it's going to be, every set is going to be a subset of itself. So A is always a subset of A, right? That's always given because every element in A is also in A, right? Pretty standard. And, there's clearly not going to be any other subsets, right? Because there doesn't exist any other sets that are subsets of capital A. Because if they're subsets of capital A, they either have to have, nothing in them, like the empty set, or they have to have the objects 0 and 1, right? And of course, the order doesn't matter. So this subset here, 0, 1, the set containing the element 0, 1, is the same as the set containing the elements 1, 0 in that order, right? So the order doesn't matter, repetition doesn't matter. So ultimately, there's nothing else here, right? And so that's how the power set works, right? It's just a set of all subsets of a given set. Again, there's a lot of set, subset, set. I'm just using these words. So hopefully you can follow it. If not, then I do advise you to sort of pause and have a think about this for yourself, or go and have a look online for a little bit more about this power set. But hopefully that makes sense. So the power set of a set is just the set of all subsets of that set. Okay, and remember a subset of a set. So A is a subset of B. If every element in A, every object in A is an object in B. Okay, right. So obviously we can also have a set of sequences or tuples or even ordered pairs, right, which is just a two-tuple. Okay, so we say that the set, well, in this, another example would be where we can effectively have sets of sequences and things like that, is where we might have, for example, a set of ordered pairs, whose elements are zeros, effectively, or ones, right? So effectively, if we wanted to find the set of all ordered pairs whose elements are either zeros or ones, right, then we have four options, right? So that's obviously going to be a set of ordered pairs. So the first ordered pair we could have is just 0, 0, right? So that's just, because it's an ordered pair because it has effectively a sequence with two elements inside it, right? So it's a finite sequence, it's a tuple, and it's a two-tuple because it has two things inside it, right? And so in this case, I've just chosen to put all zeros in there, right? And so effectively, this is just one ordered pair that contains zeros, right? And so another possibility might be something like 0, 1, right? And so in this case, I've decided to use 1, 0 and 1, 1, right? And that is actually different to the ordered pair 1, 0, right? So those two things are different. So I need to include this as a separate element, okay, in my set of all ordered pairs whose elements are composed of zeros or ones, right? Or whose elements are zeros or ones, right? And the final possibility is just me having the set, the ordered pair 1, 1 like that, right? So if this lets me finish this off, right? Okay, then there we go, right? That's just sort of an example as to when we might put, for example, ordered pairs inside sets, and you might be familiar with these sort of ordered pairs to represent things like coordinates and points in sort of the XY plane and things like that. Okay, so this does come up actually. Okay, this sort of sets of ordered pairs, for example. Okay, and even other things like ordered tuples and sequences and sets of sets, they do come up. Okay, so it's not purely theoretical, and obviously all of this is going to have applications in theory of computation, which is why we're looking at it. Okay, so now we need to talk about the Cartesian product. Okay, so that's really the other big idea you need to get from this. Okay, so if A and B are two sets, then we can define the Cartesian product as follows, right? The Cartesian product, right? Or sometimes you might call this the cross product. I don't really think I've ever really seen that notation because cross product obviously is also talking about cross product of vectors and things like that in linear algebra. But sometimes you might see it sort of as a cross product of sets. So cross product of the set A and the set B, right? And sometimes you might write this as literally as A cross B. Well, it is actually written as sort of an A cross B. So that's how you might write the Cartesian product of A and B. So if A and B are two sets, then we can define this thing called the Cartesian product or cross product of these two sets, written A cross B like that, right? And what is it? Well, effectively, it's the set of all ordered pairs. So this is the set, is the set of all ordered pairs, right? Wherein the first element is a member of A, right? So wherein the first element is a member of A, and the second element is a member of B, right? And the second is a member of B. Okay, so let's look at an example here, right? So let me just introduce the set A, which I'm going to effectively just fill up with numbers 1 and 2. Okay, so there's a set with the objects or elements 1 and 2. Okay, so we're going to say let A be that set, and let B be the set containing the letters or elements or objects X, Y, and Z. Okay, so it's a set of 3 objects, namely X, Y, and Z. Okay, then, okay, A cross B is going to be another set, right? So this will always give you another set, and this time it's going to give you a set, okay, of effectively all ordered pairs whose first element come from A and second element come from B. Okay, so an ordered pair is obviously a two-membered sequence. Okay, so the first ordered pair you might have is something like 1 followed by X, okay? This always has to be from A. This always has to be an element of the set capital A. This always has to be an element of set capital B. What the element is up to us, okay? And we basically just list all possibilities in a set. That's what the Cartesian product is. And it's actually quite useful, okay? This is actually something we use sort of implicitly in many senses at high school level, and you sort of realize that you used it a lot later on, okay? But for now, let's just not worry about that. Let's just think about the theory, okay? So the Cartesian product is a set of all ordered pairs such that the first element of the ordered pair is from A, in this case, because A cross B. So the order here is A first, then B, which means the first element will be from A, second element will be from B. If it was B cross A, that's different, okay? Because that's going to give us the ordered pair such that the first element is from B and second element is from A. So that's flipped, and the order of ordered pairs matters because the order of sequences matters. Okay, the set of all ordered pairs, so the first one you might have is 1x, then you might have 1y, right? You just decided to change this to a y, and that's different to 1x, because instead of x, it's y. Then you might have 1z, then obviously you can have 2x, 2y, and finally 2z, okay? And that finishes off our set there, okay? Right, so hopefully you can see how I've constructed this set. This is the Cartesian product of A with B. Okay, so the cross product of two sets is a set of ordered pairs whose first elements are from the first sort of set that you did the cross product with, and the second elements of those ordered pairs are from the second set that you did the cross product with. Okay, so this is effectively, I mean, hopefully you see what I've done here. If not, again, highly advise you to stop, have a think about it, or just sort of look elsewhere if you need to. Now we'll talk a little bit more about the Cartesian product. Okay, so obviously in this case we've done the Cartesian, we sort of performed the Cartesian product using only two sets, but we can generalize this. Okay, so we can, in general, define a Cartesian product of k sets. Define a Cartesian product of k sets. Okay, and obviously, and you might denote these sets as sort of A1, A2, A3, A4, all the way up to AK. Okay, so in this case, obviously k was 2 in the case that we just did for the example, right? And so we only had two sets, A1 and A2. We labeled A2 capital B instead. Okay, that's really all we've done. But we can generalize this. We can perform the Cartesian product on k sets. Okay, so you might think, how does that work? And it works in a very similar fashion, right? So written effectively A1 cross A2 cross A3 cross all the way up to cross AK. So it's quite a lot of crosses there. And effectively, what is this? What is this cross product of k sets, right? Well, it's effectively the set consisting of all k tuples. Okay, so it's the set consisting of all k tuples, right? Where effectively the elements of those tuples, so we say a subscript little I, are elements of the capital AIs. Okay, so what this means, obviously for I in the set 1 all the way through to k, right? So effectively, this sort of cross product of k sets is just another set, and in that set you're going to have k tuples. So you're going to have sort of elements A1, A2, A3 all the way up to AK. So those are k tuples, so they're finite sequences with k elements in them. Okay, and effectively the only requirement here is that this element A1 has to lie within our set capital A1. This element A2 has to lie within the set capital A2. A3 has to lie within the set capital A3, and so on and so forth. And then you basically write down all the possibilities that we could make effectively by all the possible k tuples we can make, whose first elements are in capital A1, second elements are in capital A2, third elements are in capital A3, and so on and so forth. Right? Basically, the set of all possibilities of these, right? So A1, A2, all possibilities of AIs from those set capital AIs, effectively. Okay, so that's really all it is. So there's just a set of k tuples such that effectively the ith element of that k tuple, the ith object inside that k tuple, is an element itself of capital AI, subscript I. Right? Okay, hopefully that makes sense. It's quite a complicated idea, but I should have an example of something like this. So we have an example for k equals 3, which is obviously just a slight extension from k equals 2. So in k equals 3, we can define, obviously, from before, keeping the sets keeping A equals the set containing the objects 1, 2, B equals the set containing the objects x, y, z, as before. Sorry, that should be as before. Right? Then effectively we have the A cross B cross A. Right? That's just going to be another set. Okay, we already know what A cross B is, so that's effectively just going to be our set from before. So that was, what was it? We had the set containing the ordered pairs 1x, 1y, 1z, 2x, 2y, 2z. And now we're going to cross that with A again. Okay, so effectively, for each of these, we then want to add in a third element, right? Because we have three sort of sets we're crossing here, we're going to have three tuples in our set. It's going to be a set of three tuples, such that the first element is from A, okay, so that could be a 1 or a 2. Second element is from B, so that could be x, y, or z, and third element is from A. So obviously here we're going to have 1x1, right? Then you can have 1x2, then you can obviously also have 1y1, 1y2, right? 1z1, and then 1z2, right? And then you continue, and then now you have the 2, so 2x1, 2x2, right? And so you can already imagine, like, sets here can get the size of these sets can get pretty big pretty fast. So 2x2, and then we're going to have 2y1, right? And then 2y2, and then 2z1, and then 2z2. Okay, so this is actually what we get when we do this sort of order 3 Cartesian product on the set A, B, and A in that order. So A cross B cross A in that order. Okay, remember the order there does matter. Okay, because it changes effectively the ordered k tuples that you get, the ordered 3 tuples that you're going to make. Okay, because if it was A cross B, then you would get 1, 1x, 1, 1, 1, 2x, and so on and so forth. So effectively the position, so the elements of your sort of k tuple that are sort of from the set capital A would change, right? In that case, it would change from the third element, which is here, to the second element, which is here. Okay, so the order in which you do this Cartesian product does matter. Okay, so A cross B cross A is not the same as A cross B. Okay, so just keep that in mind as well. Right, but hopefully you can see how we generated this set. In other words, it's effectively just A cross B, which we can define as another set, C crossed with A, right? And so effectively, once you have that, then, yeah, I mean, once you write it that way, then you can effectively just reduce it to sort of k equals 2, right? Because if I were to write A cross B as another set C, then what I'm really doing here is C cross A, which in this case is going to be a set of effectively ordered pairs, right? Where the first element of the ordered pair is from the set C, which in this case is just going to be A cross B. So that itself is going to be an ordered pair. So you have an ordered pair followed by effectively one element, which effectively just makes an ordered triple. So that's why this that's effectively another way you could do this. You could effectively just inductively build it up from 2 to 3, right? And then because effectively, if you wanted to build it up from 2, if you had A cross B is equal to something, and you wanted to find out A cross B cross C, for example, then you can just find out what this is, and then you effectively have D, and you can cross it with C, and then you're back to sort of the two k, like the case with k is equal to 2, right? So effectively, you can just build this up for any k sort of inductively, right? By just finding sort of the cross product of sets pairwise. So that might be another way of doing things if you want to do it that way. But yeah, I mean, I think both ways are fine. Okay. Right. Now, obviously, in this case, we do the Cartesian product of sort of two different sets. So A and B are two different sets, right? So you did A cross B cross A. But we can take the Cartesian product of a set with itself, right? There's no limitations on that. So for the Cartesian product of a set with itself, okay, we use the shorthand. So there is a shorthand for it. We use the shorthand effectively A cross A cross A cross and so on and so forth cross A, and so that k times. So imagine that was just a sort of k a's followed by sort of just the crosses after each a, right? So the Cartesian product of a set just crossed with itself k times can effectively also be written as sort of the set a to the power of k, right? And so we can define this notion of effectively raising a set to a power, effectively as just the Cartesian product of that set, okay? And so a common example that you might see is, for example, n squared, right? So n, as I'm sure you're familiar with, is a set of natural numbers. And we also looked at that in the sets video that we in the last video I made on sets, prerequisite to theory of computation. So this capital N here is just the natural numbers, right? So it's just the natural numbers. But you might think, what does it mean for it to be squared? And now you know, right? It's the Cartesian product of the natural numbers with itself, okay? So the set n, so the natural numbers crossed with themselves, we'll take the Cartesian product of the natural numbers with themselves, is just effectively n squared, the natural numbers squared, effectively. This is just the sort of shorthand notation that we use to represent that set, n cross n, effectively. Okay, so this set, the set n cross n, consists of all, right, but this is effectively just the definition of the Cartesian product, but applied to the natural numbers. So it consists of all ordered pairs of natural numbers, right? Of natural numbers. So another way you might write this, so we may also write this as effectively n cross n, right, like that, which is effectively just a set of all ordered pairs ij, right, such that, this is just the notation that we had last time, effectively for the finding sets with, effectively, what the objects in your set are going to be, and then the property that you're going to use to effectively produce those objects, okay? So it's effectively such that I and j are greater than or equal to 1, okay? So, and I think we really should specify that they're in the naturals. But I don't think the text did that, but I mean, obviously, it's kind of inferred here, and in general, the context is there anyway. But if you want to be specific, you probably would have to say I and j are in the naturals. Obviously, any natural number will be greater than or equal to 1, or greater than or equal to 0, depending on how you define them. But we'll define the natural numbers to start at 1, so the 1, 2, 3, 4, 5, and so on and so forth. Right, so effectively, n cross n is just by definition a set of all ordered pairs, okay, such that the first element of the ordered pair is just any natural number, and the second element is another natural number. So it's just a Cartesian product of the set with itself, right? And so yeah, you might also see it written sort of in this form here, right? So this is more concise because it's obviously going to be an infinitely sized set because it's infinitely many natural numbers. So the choice of my first element is infinite anyway. So there's infinitely many possibilities for what I could be, and there's infinitely many possibilities for what j could be. So obviously this set is going to be infinitely large, okay? So n cross n is going to be infinitely large. And you might see it written in this form. And obviously it's obviously implied that I and j are elements of the natural numbers as well, okay? So this has basically just been a video on sequences and tuples, okay? And so we've covered, effectively just going back through everything, we've covered what a sequence is, how we designate a sequence, how we sort of introduce a sequence, the difference between a sequence and a set, so obviously the order matters, okay, so repetition of terms also matters, effectively some terms, so obviously finite sequences are called tuples, sequence with k objects in it is called a k-tuple, and a two-tuple is an ordered pair, and effectively the idea that you can also have sets inside sets and sequences inside sets, so we saw an example of where sets are inside sets with a power set, so the set of all subsets of a set, of a given set. Then we also looked some other examples, just an arbitrary example here, the set of all ordered pairs whose elements are zeros or ones, okay, that's an example you might include, so sets of ordered pairs. Okay, and then we also introduced, lastly, the Cartesian product, okay, of two sets, did an example with it, generalized it to k sets, okay, which is something that you'll see in maths come up, and I assume it's going to be useful here since it's introduced in the textbook. In the theory of computation as well. Okay, and so we have the Cartesian product of k sets, right, which effectively works very similarly to Cartesian product of two sets, just generalized. And then we looked at an example with k is equal to 3, and then looked at sort of notation for the Cartesian product of a set with itself k times, just effectively that set to the power of k. So now we understand what it means for a set to be raised to effectively a power in some sense. And then we looked at a very common example, which is n squared, so the natural numbers squared, effectively the natural numbers cross with themselves, the Cartesian product of the naturals with themselves. And we also looked at another alternate way to write the Cartesian product of the naturals with themselves in sort of this set notation here. Okay. And obviously another example that you'll see quite a lot is r squared, so the real numbers squared. Okay, effectively just the set of all ordered pairs where the first and second elements are just real numbers. So that's even, you would imagine it to be an even sort of larger set, really, in some informal sense. Okay, I mean, the sizes we can get into sizes of infinity at some other point in time, but effectively, as long as you understand how this is defined, so this is effectively just the set of all ordered pairs of real numbers, such as the first, of all ordered pairs of real numbers, really. So the first and second elements of those ordered pairs will have to be real numbers. Okay, or objects of those ordered pairs. Okay, so that's that. Thank you guys very much for tuning in. I'll see you guys next time. That has been Prerequisite video on sequences and tuples. Thank you guys very much for watching. Goodbye.